Metals and alloys is a very short section, so there's not much to go over, so let's go. So first we're going to focus on metals before we talk about alloys. And so metals have a low electronegativity, as we talked about with periodic trends. They tend to have 1 to 3 valence electrons or so, and that's, the basics from, again, previous unit. They have a crystalline structure. So what that means is that it kind of looks like a lattice structure, very similar to ionic compounds. You can see in this diagram over here, they're very patterned out, evenly spaced, all of the metal ions, right? And it's only metal. There is no nonmetals, because otherwise it would have been an ionic compound. You also have the delocalized electrons I've mentioned before, so you have the ones over here, and they can flow around freely. That's also known as the sea of electrons, so you'll see both of those terms. Their melting points can range because of the valence electron amount that they have. Usually it's pretty low, relatively, and we know that they can conduct in solid and liquid form because, again, the electrons can free flow around. Now, let me pose a quick little mini your turn. Why not gas? So think about it first before I do. Ready? Well, gases are really far apart. The atoms of a gas. So if I had metal gas floating around, the electrons won't really be flowing near each other because you don't have this nice positive ions in very close proximity, so therefore the electrons can freely flow around. The atoms would be moving around a lot, so that's why. The main reason why, anyway. Cool. And so they're also malleable. So malleable means that you can use a hammer, you can easily, smash it. It's also ductile, meaning I can make it into a wire, and they're pretty much, all of this means deforming in some way. And even when we deform it in some way, they can still remain bonded. Obviously, to a point, there's always a stress point at some, edge. But in general, I could deform it and it's perfectly fine. And then the last characteristic, it has luster, meaning it has some shine. Alrighty, alloys next. So alloys, by definition, are a physical, homogeneous mixture of elements. We focus on metals, and they have properties of a metal. Obviously, if they're made out of metals, they're going to have properties of a metal. And so we have two main types. We have substitutional and interstitial. And so these two main types are based on the size of the atoms, as you can see in these diagrams. So we're going to talk about each real quick. So in substitutional, they're going to have similar radius. So you could see that the copper here has a similar radius to the nickel's radius, because you could see it's barely any different, but they are different. And you could see they are spaced out in this mixture. Again, it's a homogeneous mixture. This is brass. And so anytime you've used a brass product, they literally are made out of nickel and copper, with copper randomly dispersed in that mixture. Interstitial, on the other hand, is when you have atoms that have different radii sizes. So you can see here the copper is really tiny versus the iron that's in gray. And so interstitial literally means the space in between the different atoms. And so since we have the iron having these tiny little spaces, you can put the carbon atom in between because it would fit. And so that's what interstitial is. So again, substitutional has a similar radii compared to each other, versus interstitial has significant difference. Make sure that you could draw this if you were asked to. So if they said, hey, you have this element and you're going to make an alloy and it's substitutional, make sure that you draw your substitutes being slightly different. Versus an interstitial, make sure you have tiny ones and larger atom sizes. So make sure you could do that. So let's talk a little bit about properties. So they can be stronger in alloys compared to metals by themselves. And so that means because they're stronger, they're less malleable, less ability to deform, because again, they're stronger. They could technically be more brittle too, because they can slide in different layers. In general, they'll have a higher melting point just because of the way that they're interacting together, and just as similar to metals, they can conduct electricity. And so make sure that you know those properties. And then alloys. So like I said, they can keep layers of metals. And so pretty much an alloy helps these metals from sliding off each other. In ionic compounds, you can have some of the ion layers that we saw in the cube shape slide from each other, which is why they can break pretty easily, versus alloys. Alloys are very rigid, again, less malleable, so it's going to be harder to do that. All right, here is a quick your turn. Have your periodic table out, pause this video, and try these questions out. Ready for the answers? Here we go. Now I will go off the bat that these answers are pretty subjective because it's going based off radii. And it's, again, kind of estimates. Some answers will be better than others depending on how the question is asked. These are two random problems I happened to find just to, have a question for this section. But honestly, the College Board questions in terms of sizes will be more concrete of an answer, for sure being substitutional or for sure being interstitial, which is why you can see some of my wishy-washy answers here. So we have these different elements here, and you want to find them on the periodic table. Then, if you add these separately into this alloy that was mentioned, pretty much you have to say, hey, substitutional or interstitial. And so for zinc is very close to copper, which is why it would be substitutional, because you're pretty much, again, similarly sized in terms of radii. In platinum, we'd say it's probably interstitial, just because platinum is not really close to the elements that are mentioned here. So it would probably be interspersed randomly in random spaces there is. Now, I did write here, you could argue substitutional. If you say that mercury is really close to platinum, then you could argue that. So that's why I said there is some subjectivity to it, which is why a question like this on the AP test would be more concrete of an answer. Tungsten small, they're compared to like some of these, so it could be interstitial. Then for number 2, carbon, definitely interstitial. It's so far away from iron and chromium. Nickel's bigger, and so even though it's bigger comparing iron and chromium, it's still probably interstitial. Again, very subjective there. And then chromium's a trick question because it was literally in the problem. Yeah. And that is it. This section, nice, sweet, short. We love sections like this. All right. Have a good rest of your day. Bye.